series and parallel LCR circuits. Here we study the basic phenomena of resonance in electrical circuits using LCR series and parallel circuits. The experiment is based on the principle of resonance. Resonance in electrical circuit is nothing but the condition at which the inductive reactance equals the capacitive reactance. Inductive reactance represented by XL is directly proportional to the applied frequency, is nothing but the impedance offered by the inductor to the flow of AC current. When XL is equal to XC, the corresponding frequency is referred as resonant frequency. This resonant frequency depends on the values of inductor and capacitance chosen in the circuit. So, the combination of L and C will define a definite resonant frequency, and the corresponding circuit is referred as resonant circuit. When these components, the inductor and capacitances, are connected in series, the circuit is referred as series resonant circuit. Similarly, when these components are connected in parallel, results in parallel resonant circuit. These circuits are used to select a desired band of frequency or to reject unwanted frequencies. Hence, resonant circuits are very important in communication systems. Let us start with series resonance circuit. Here, all the elements are connected in series as shown in the figure, along with a milliammeter and AC source. So, the experimental setup requires a function generator which generates various frequencies, various signals of frequency ranging from 1 Hertz to 100 kilohertz. So, we connect this function generator to the experimental setup board, and we choose the value of L as 0.1 Henry, value of C as 0.01 microfarad, and the resistor 1 kilohertz. All are connected in series with a milliammeter and function generator. So, this chosen value of L and C will give a natural frequency of the circuit as given by the equation 1 by 2 pi root LC, turns out to be 5 kilohertz. In the function generator, we select the range as 1 kilohertz, so that the applied frequency range is also in the same as that the natural frequency of the circuit. Set the amplitude to be maximum, amplitude of the signal to be maximum. Now switch on. So, the function generator is giving signals of various frequencies ranging in the frequency range 1 kilohertz, and we have the circuit consisting of inductor, capacitor and resistor connected in series. Each is generating its characteristic frequency of the order of 5 kilohertz. So, initially, as the frequency changes, XL is greater than XC. The inductive reactance is greater than capacitive reactance. Hence, the circuit behaves more inductive. Hence, you find increase in the value of current as you increase the frequency. So, I am increasing the frequency in steps of 1 kilohertz, 2 kilohertz, 3 kilohertz. You observe that the current through the circuit, a series circuit, is also increasing. But when you reach 5 kilohertz, you observe the current through the circuit reaching maximum. See, at 5 kilohertz, the current is 6.42. If I move further, it is decreasing to 6.15. And previously, before 5 also, 5 kilohertz, the current is less than 6.46. So, the maximum current through the circuit is 6.52 and the corresponding frequency is noted. It is coming around 4.8 kilohertz. Further increase in the frequency will reduce the current through the circuit, because now the circuit is becoming more capacitive than inductive, and you observe that current is decreasing continuously. Okay. So, when the current is maximum, the corresponding frequency is referred as the resonant frequency, at which the circuit is purely resistive, because inductive reactance is equal to capacitive reactance. Hence, impedance of the circuit is purely resistive, that is minimum resistance of the circuit. Hence, the current through the circuit is maximum. So, as it is clear from the graph, you observe that as the frequency is increasing, the current is also increasing, reaching a maximum and then decreasing. So, before the resonant frequency, the circuit is more inductive. Beyond resonant frequency, the circuit is more capacitive. Hence, the characteristic graph. At resonance, current is maximum in series circuit. So, theoretically, resonant frequency is given by the formula 1 by 2 pi root LC. Substituting the value of chosen L and C will give you 5 kilohertz. And experimentally, from the graph, it is coming around 4.8 kilohertz. Now, the same graph can give you further details or further results. Further important parameters of the LCR circuit, such as quality factor. Quality factor of the circuit is the figure of merit used to measure the ability of the circuit to discriminate between different frequencies, and it is given by, in terms of inductive reactance omega naught L by R, or in terms of capacitive reactance 1 by omega naught C R. or we can also define quality factor in terms of bandwidth practically from the graphical observations. Quality factor is given by f naught by bandwidth, where f naught is the resonant frequency, bandwidth is the range of frequency for which the response do not drops below 70.7% of its maximum value. So, the range of frequency is selected by drawing a line across the graph corresponding to I maximum by root 2, and these 2 points on the x-axis abscissa are referred as the cutoff frequencies. Here these are called cutoff frequencies because the power delivered to the circuit or power delivered from the circuit at this particular frequency is exactly half. So, this is the range of frequency which can be selected by this particular circuit, and which is very useful, wherein the power delivered is exactly half. So, from the graph note down the bandwidth of this particular circuit, in which the value of chosen L is 0.1 Henry and C is 0.01 microfarad. Note the bandwidth, note the resonant frequency, and calculate the quality factor using the relation f naught by bandwidth. So, it is also given theoretically by 2 pi f naught L by R. So, here the role of resistor comes into picture. So, the value of R will decide the shape of the curve, resonance curve. So, sharpness of differentiating the frequencies, the range of frequency depends on the value of R. Higher the value, higher will be the sharpness of the curve, and hence the quality factor thus decides the quality of the circuit to discriminate the frequencies, various frequencies in the within the range of bandwidth. This procedure is repeated for the parallel resonant circuit by connecting the capacitance in parallel with the same components, with the same set of values. We connect the capacitance in parallel, except the capacitance in parallel with the other two L and R, and we repeat the experiment in the same step because the resonant frequency of the circuit is same, because we have not changed the values of L and C. So, the circuit resonates at the same frequency, but the current through the circuit, you observe it is maximum initially. So, at 1 kilohertz initial value of applied frequency, you see that the current is showing maximum. So, as the frequency is increased, the current is decreasing, and reaches maximum reduction at again 4.8 kilohertz. So, this is the minimum current flow through the circuit, and it is again happening at 4.8 kilohertz. So, that is the resonant frequency. So, where Again XL is equal to XC. As you increase the frequency, you observe that current is again increasing and reaching maximum. So, the characteristic graph as seen shows initial decrease in the value of I as the frequency is increasing, because the circuit is more capacitive initially when it is in parallel, when all the components are connected in parallel, then reaches a minimum at which XL is equal to XC. Then onwards the circuit is more inductive, hence current through the circuit increases. So, resonant frequency is noted from the graph. Bandwidth of parallel resonant circuit is obtained by drawing a line, horizontal line corresponding to I minimum into rho 2, and the corresponding x intercepts are taken as F1 and F2, lower cutoff frequency and upper cutoff frequencies. Hence bandwidth is determined. The quality factor of the circuit is obtained graphically using the relation F0 by bandwidth. So, theoretically again the expression for quality factor is 2 pi F0 L by R. Again it depends on the value of R. So, higher the value of R, higher the sharpness of the curve, hence the higher quality factor of the circuit. So, from the experiment, the resonant frequency of the circuit, which is dependent, which we came to know that it is dependent on the chosen values of L and C. So, as and when you change the values of L and C, the resonant frequency changes, and quality factor of the circuit can be changed by changing the value of R. So that was the important observation, and these circuits are used in tunings various frequencies such as in communication systems. So, when we are varying the value of C, means we are tuning, actually when we are tuning the radio, we are tuning the values of L and C internally. So, internally the circuit is selecting the range of frequencies within the bandwidth which is decided by the quality factor of the circuit. So, the results of this experiments are tabulated as important observation that resonant frequency depends on L and C value, and quality factor of the circuit depends on the resistance used in the circuit. So, these are the important features of the LCR circuit, which is based on the principle of resonance. The related viva questions are listed as follows.